In this session, we will be dealing with two important concepts of statistics. One is the world of correlation, the other being regression. On a broad scale, correlation talks about the strength of relationship between two variables. Now, our major intention or major takeaway from this session should be, how do I link up the relationship between the two variables, and if there is some kind of relationship or dependency between the two variables, how do I use the information or the relationship to predict one given the other. So correlation is talking about understanding the relationship between the two variables. Let's say I want to find out whether there is some kind of relationship between profits and sales. That is the data I would like to work out with, right? To help you understand that concept, I want to look out whether there is any kind of relationship between profits and sales of a company, of different companies. So the moment I know what should be the sales, what is the sales, can I predict what could be their profits? So that is the one which I would like to look at. So whenever I want to compare the relationship or identify the strength of the relationship between the two variables, I am resorting to the correlation kind of analysis. And probably given the sales, if I want to predict what could be the profits, so predicting one of those variables given the other is what is the process of regression. So before we get into that particular process, to understand correlation, even we are looking at a term called covariance. It is nothing but, it is also a measure which is talking about how one variable is moving with respect to the other. When one of the variables has increased, what has happened to the other variable? Did it decrease, or did it increase at the same rate as the first variable, or did it increase or decrease at a smaller rate or at a larger rate, or is it more or less flat? So all these kind of, the way the second variable is moving with respect to the first variable is an indication of covariance. So what we look at is the average product, the average product of differences of each of the variable from their corresponding means is what is the way we define the covariance. So I'll try to apply these things on the data so that the things become more clear for us. So for this I have taken one simple data set wherein I have captured the profits of some 100 companies in the pharmaceutical industry along with their sales in a particular year. So at a particular point in time, I have captured the profits as well as the sales of some 100 companies in a particular industry itself. Now I want to see, is there any kind of relationship between the profits and the sales? So before getting into that particular process, we are first trying to find out the covariance. So for finding out the covariance, I really require as a formula, what I require is x minus x bar into y minus y bar, which is the mean of x subtract from each of the x, the mean of y subtract from each of the y, multiply them and add up for all the data whatever we have, add that up and divide by n minus 1. Generally the division by n minus 1 is more associated because we work with sample data, but if we work with the entire population data, then probably instead of n minus 1 we can use n itself. So using this specific formula, we can find out the covariance, and once we find out the covariance, we can get into the process of finding the correlation between those two variables. So let me get into this process here. So mean of profits. I want to find out the mean of profits, wherein I'll simply take the average. I'll take the average. So probably you could add up all these numbers and divide by 100, which will give me the average. So the average profit is somewhere around 98 bucks. Whereas if I take the mean of sales, right, if I take the mean sales, this is coming out to, I'm taking the average. If I take the average of sales, this is somewhere around 1016 bucks. Fair enough. So these are my X bar and Y bar. Right? I can take anything as X, I'll take anything as Y for the time being. So the mean of the profits is 98 and mean of sales is 1016.04. Now, okay, let me, by default itself, let me take this as Y and let me take this as X. So the next thing I am interested in finding out is X minus X bar, Y minus Y bar. So I'll find out X minus X mean, which is nothing but X bar. Right, I find out X minus X bar, which is X minus X mean. So each value I subtract the mean from it. I subtract the mean from it, and this is what I call as X minus X bar. Okay, there are some positive values, there are some negative values. So this is what is coming out as each value I am subtracting the mean from it, which is X minus X bar. Similarly, I will do Y minus Y bar. Right? So X minus X mean, which is probably I should call this as Y minus Y mean. So here I'll take X minus X mean, X bar. So X minus X bar, X is the sales of each of the company minus the mean sales. Okay, X minus X bar. This is what is the case for all of them. Then, as per the covariance computation formula, I need to multiply X minus X bar with Y minus Y bar. So probably I'll call this as product, wherein I am multiplying X minus X bar multiplied by Y minus Y bar for each one of them. So this is the product I am getting, X minus X bar into Y minus Y bar. Then I have to add up all of them and divide by n minus 1 to arrive at the covariance. So I am getting the covariance here as the summation of all these things, divided by 99, because I have 100 data points, n minus 1 is what I have to take. So I am dividing by 99, giving me that the covariance is some 354,000. This is what I am getting as the covariance. Of course, if I am working out with a formula of Excel also, I don't need this entire thing, but if at all, just to understand the concept, if at all at some point you are required to derive this particular formula, it's better that you know how we come to this computation of covariance. Each of the observations of the X and Y, the variables, we subtract its corresponding mean from each of the observations, multiply it pairwise, add it up and divide by n minus 1. Otherwise, I can even use the covariance formula between the two sets of values, this comma this comma this. This is the covariance I am using between the two sets of variables, which is also coming out to the same number. So either I can use a formula kind of an approach or the procedure kind of an approach, but in whatever the case, the covariance between the two variables is coming out to 354,729. Now the problem here is it high? Is it low? What is it? What does this 354,729 mean? That is where the basic problem lies with the covariance. It's not meaningful because it is very much sensitive to the scale. Probably if I have large data, large data and even very high values physically, absolute values are high, automatically the covariance could result into a very large value. So there are no bounds to it. Probably it may be going up to plus infinite or it may be going up to minus infinite also. So there is no way I can typically say whether the covariance is high or low. That is the reason we are going one more step further in terms of identifying what is called as correlation, because covariance, though it is talking about the movement between the two variables, when one is moving in one direction, what is happening to the other, but at least what I can interpret from covariance is, if it is positive, probably I can say that both the variables are moving together in the same direction. If it is negative, we can say that both the variables are moving more in the opposite direction. At least to some extent, the sign can be a useful thing, but I cannot do anything more than the sign there. The absolute value of the covariance doesn't give me any kind of an indication. That is where we are getting into what we are calling as the correlation. Correlation probably is a much better interpretation of covariance, because the correlation is talking about the strength, because what it does is it normalizes the covariance by dividing by the standard deviation of x and the standard deviation of y. It's a kind of a normalization relationship where the covariance is adjusted by dividing by the standard deviations of each of them. So because of that reason, we find that the correlation value will always lie between -1 to +1 only, not like minus infinite to plus infinite kind. It always lies between the -1 to +1 itself. So because of that, we can very well establish the strength of the relationship between the two variables. So if I look at it here, so I need the standard deviations now. How do I get the standard deviation? X minus x bar whole squared. Instead of doing x minus x mean like this, okay, x minus x mean squared, right? I can take x minus x mean squared. So this number I can take it as squared. Similarly, I will take y minus y mean squared. So here also I will take y minus y mean squared. Alright. Y minus y mean squared. Okay. Now, when I am looking at the standard deviation of x, which is nothing but I add up all the x minus x mean squares, I add up x minus x mean squares divided by n minus 1, that is 99. This gives me the variance, and I take the square root of this particular variance. It gives me the standard deviation of x. So the standard deviation of x is around 1597 units. The same logic if I am applying to y, I can very well use the formula of standard deviation also. Right? If I am working purely with Excel, I can even use the formula for standard deviation. The standard deviation of y. I don't need to do this entire process also. I could have directly selected this saying standard deviation of y, which is coming out to somewhere around 278. Now from here, if I want to find the correlation, it is nothing but the covariance divided by the multiplication of the individual standard deviations. That is what is giving me the correlation, which is coming out to almost 0.79 or 0.8, close to 0.8 is the correlation between these two variables. The profit versus the sales, the correlation between them, probably I could verify it using the formula of Excel also, where I directly can use the correlation between the two variables. I can select the correlation between the first variable and the second variable. The correlation between the two variables coming close to 0.79826. So either I can find out the covariance divided by the individual standard deviations just to understand the concept part there, or I can directly find out the correlation part. Now this correlation, as I said, will lie majorly between, correlation lies between plus minus 1 and plus 1 only. So that way I can very well go ahead saying if it is very close to plus 1, I say there is a strong positive relationship. There is a strong positive relationship, and if it is very close to minus 1, I can say a strong negative relationship. But when it is very close to 0, I can say that the relationship may not exist. But here, let me try to put one more thing. Here when we are talking about the word relationship, I am more interested in saying the linear relationship only. Correlation actually measures the strength of linear relationship between the two variables. There might be some kind of a non-linear relationship existing between them also, but correlation as a concept measures only the linear relationship between the two variables. So in this case, at least we got the correlation of close to 0.8, right? Now if it is very close to, or if it is, as long as it is positive, we say there is a positive linear relation, negative linear relation. Only when it is plus 1 or minus 1, we use the words as perfect positive. We use the words called perfect positive relation or perfect negative relation between the two variables. That is one way to interpret the relationship between, or linear relationship between the two variables using the concept of correlation. So at least in this case, I am seeing that the correlation is strongly positive. Though it's not perfectly positive, there is a strong positive relationship between the profits and the sales, right? Now the same thing, the same relationship can be understood through a graphical mechanism also called the scatter plot. I draw a graph between x variable and y variable. I draw a scatter plot between the two, where I take one variable x on the x-axis and the other one on the y-axis, and see how the values are scattered. And based on the pattern of the scatter, I could very well say whether they are positively correlated or negatively, which means the graphical way of representing the correlation relationship between the two variables is quite comfortable when I am using a scatter plot. Right, so let's try to draw the scatter plot and see how we can interpret the relationship between the two variables. Okay, looking at the scatter plot on this data itself, probably let me try to take the scatter plot somewhere here. I am inserting a simple scatter plot wherein I am adding I'll call it, let's say, profit versus sales, and on the x-axis I will take sales. I'll take sales on the x-axis, and I'll take profits on the y-axis. I take sales on the x-axis and I take the profits on the y-axis. And when I am trying to plot the graph, let's see how is it coming out. Where is our graph? Alright, so this is the graph between the x and y, the sales as well as profit. Now look at the pattern in the graph. We see that on an average, as the x values are increasing, the y values are also increasing, and vice versa. So you see that if at all I am trying to draw one line out of this graph, that line will be a kind of an upward sloping kind of a line, because we are seeing that probably if I want to draw one smooth straight line out of it, joining almost all the points, it looks as if it is an upward sloping kind of a line. So wherever I am seeing this kind of upward sloping kind of a line, I associate that to a positive relationship between the two variables. Or just in a tool like Excel, I can even try out for a trend line, a linear trend line, now which is showing that something is going up. So when I see that the trend line is going up, it is an indicator that there is a positive correlation. But all the points, if they are lying on that trend line only, then it would be a perfect positive correlation. On the other side, probably if I had seen a line, or if I have seen that as the x values are increasing, y is decreasing overall, then I could have got the correlation values as negative, and even when I had attempted a trend line, it would have come mostly as a downward sloping kind of a line. So in those cases, the correlation will be negative. So that's one way we can interpret the relationships between the two variables, either through the calculation of correlation or using a scatter plot, which is a graphical representation of the correlation. Now, the next thing I would like to see here is some kind of limitations, especially with correlation, some limitations that could come up. So one major limitation that I am looking at is the presence of outliers could distort the relationship between the two variables. What I meant by that is, let's say here, instead of 8,370 has the sales, if I make it as 108,370, or probably 88,370. Just observe, right now the correlation is only 0.79. Just one value I changed, 88,370. I am seeing that the correlation, the value has fallen quite drastically. It has come to 0.52, almost from 0.79 or close to 0.8 stage. It has come to a stage of 0.52 only, which means if there are outliers, because most of these variables are in that at the max up to 7,000-8,000 range, but one value directly going up to the around 88,000, it is treated as outlier. So wherever you have very heavy extreme values in our data, we are actually calling them as outliers. And because of that outlier, in some cases when there is no relation, it looks like a relation is existing, or when there is a relation that is existing, it looks as if the relation is not existing. So that could be a very misleading kind of analysis. So that's where what is suggested is you try to see in your data if there are any kind of outliers. There are various ways of identifying the outliers in your data, because one thing that is expected out of your data is it should be more or less close to normal. For applying the correlation or regression relationships, for applying the correlation, we should see that the data is more or less normal. And to say whether the data is more or less normal, probably I would also look out for the skewness and the kurtosis present in the data. But just as a quick lookout on the skewness, I am seeing the skewness is 3.0, which means the profits is actually containing some skewed data. And what about the sales? So we should have removed those, means there are some outliers. If the skewness is 0 or very close to 0, then probably I can say that there may not be any kind of outliers in my data. But if the skewness is so much positive, it means there are some kind of outliers. So whatever the 0.79 that we have got is also because of the presence of some of the outliers. So it may so happen that we may get something more or something less. The relationship is not a true relationship because there are some outliers that are still present in the data. A skewness of close to 0 is an indicator of no outliers present to a large extent, whereas when the skewness is very high, positive or negative, it is a clear indication that there are some outliers that are present in your data which needs to be addressed. So that is one drawback that is associated with a linear correlation kind of concept. In some cases, there is another word, let's say spurious correlation, where here we got a correlation value as, let's say 0.8. So generally it gives me a kind of a tendency to feel that there is a strong relationship between the profits and the sales of a company, which in this case might be possible. But let's say I want to check out the relationship between the profits and the height of the employees. I want to see the relationship between the profits and height of employees, or probably I want to see the relationship between the profits of the company and number of letters in their company name. Some such kind of weird things. Or the other way of talking of, I am doing my business in India, whereas I want to see the relationship between my company's sales and the GDP of some other country, say Uganda. It may sometimes come out that the correlation is 0.8. which says that there is a strong relationship between my company's revenues and the GDP of Uganda. Whereas in reality, there may not be any kind of economic meaning or economic sense because I have nothing to do with Uganda. So, what could happen is sometimes when we are depending excessively on the data may show some sort of relationship, but in reality, the relationship may not be present at all. So, we have to be really careful from the perspective of economic sense. Does this make any kind of a sense? So, whatever the relationship, whatever the correlation value that we are getting, we have to look at it from an economic sense standpoint. And as I said, correlation always measures only the linear relationship between the variables, which means if there is a non-linear relationship, it simply ignores. It may give some kind of misleading results. If there is a non-linear relationship existing between the variables, we have to be very careful even from that dimension also. So a better way of putting it is, if I get a correlation of 0, it means that there is no linear relationship between the variables. So you can't say that there is no relationship between the variables. We are only saying that there is no linear relationship between the variables. Right? Now, the next aspect is, I look at correlation, whatever the value that we have obtained, I have to do some kind of hypothesis testing on that. What is that hypothesis testing for? To make out whether the relationship is significant or not. Whatever the relationship, correlation value we have got, just to interpret whether the relationship is significant or not, we perform a hypothesis testing. And for performing this hypothesis testing, we generally take the null hypothesis always as correlation is equal to 0, which means no linear relationship exists, and the alternate hypothesis always goes as correlation not equal to 0. We are taking, if I want to test whether the relationship is statistically significant or not, I will look at the correlation equal to 0 versus the correlation not equal to 0. And now, under the assumption that the two x and y are normally distributed, right? That is where we want x and y to be almost normally distributed, means there should not be much of outliers. Skewness should be very much close to 0. So assuming that is the case, we can use the t-test. We will use the t-test to test for the significance of this correlation. So what we are saying is the t-test, the statistic that is used for this case is whatever the correlation that we have computed, R, take it as, find out the t statistic value, R into square root of n minus 2 divided by 1 minus r square. This is the t statistic which we are looking at. So compute this and compare it with a t distribution with n minus 2 degrees of freedom. A t distribution with n minus 2 degrees of freedom, because we are using two variables x and y, we are comparing it with n minus 2 degrees of freedom. So going with our numerical, what should be the t value for our numerical? Let me see what is the t value for this numerical. So the t value is the computed correlation times n square root of n minus 2, because n we have 100, I'll take it as square root of 98 divided by square root of 1 minus r squared. R is something which we have computed, so I am getting it as 1 minus r squared. The computed t value is coming out to be 13.12. The computed t value is coming out to be 13.12. Now I will compare the standard t value with 98 degrees of freedom, probably at 5% significance level, right? 5% significance level and 98 degrees of freedom. The critical t value, okay, so the critical t value is, if I am looking at the critical t value with 5% or 5% significance level and 98 degrees of freedom, is 1.98. So the critical values are minus 1.98 to plus 1.98. So if my calculated value, what is the calculated value here? 13.12. If my t statistic, which is the calculated value, is lying within this critical interval, so this is arrived based on two aspects. One is the level of significance or the confidence level, and the other one is the degrees of freedom, which is n minus 2, the sample size minus 2. So if at all I am seeing that my computed t statistic is lying within this interval, I do not reject. So lying within it, do not reject the null. But if my computed t statistic is lying outside this interval, I can reject the null hypothesis and go with alternate hypothesis. So because this 13.12 doesn't fall within this range, I can reject the null and I am going with the alternate hypothesis, saying the correlation is not equal to 0. So it is significantly different from 0, which means a decent linear relationship exists between the two variables. So you should not stop with just computing the correlation value. It has to be extended by one more step in terms of testing the hypothesis for it and seeing the test in terms of testing the hypothesis for it and seeing whether the relationship is statistically significant or not. So that is one more thing we have to be comfortable when we talk about correlation. Alright. Now we will slowly move on towards the concept of linear regression and use the same example to probably go ahead in terms of interpreting or predicting the data based on the linear regression kind of a process. Now whenever we talk about the concept of linear regression, we bring in two variables, right? Just an extension to the correlation, but one thing is we have to differentiate between what is a dependent variable and what is the independent. Out of those two variables which we are looking at, we have to understand what is the dependent variable and what is the independent variable, because linear regression is a mechanism of predicting one given the other. So it is talking more and more of a dependency relationship between the two variables. So we have to identify which one is dependent on the other So identifying out of the two variables whichever we have, which one is the dependent variable and which one is independent. Sometimes we even have the names called this is explanatory variable or probably explained variable, whereas this is called as explanatory variable. What is being used to explain the explained variable. Then this is also called as endogenous variable, just for the names, endogenous variable, whereas this is called as exogenous variable. So basically independent variables are the ones which are determining the dependent variable. So that's where this is also called as predicted variable, the variable which is getting predicted, whereas this is called as a predicting variable. So linear regression is basically the first step as a part of linear regression process is to identify which is a dependent variable and which one is an independent variable. Now once that part is identified, we are assuming a relationship between x and y. So here I am taking generally y as the dependent variable and x as the independent variable, though it is not mandatory. Just to streamline the convention of usage, we are taking y as the dependent variable and x as the independent variable. So a straightforward way of representing the regression equation or the relationship is y equal to a plus b times x. So typically each and every y I write as a plus b xi corresponding to its x value. I am trying to find the y value by associating some values to a and b, and because there could be some kind of an error in the process, because I am trying to find out, let's say I have 100 records. Based on the analysis of the 100 records, based on trying to write them in this particular form of a plus b xi, I am trying to find out some values for a and b which try to minimize this particular error between the predicted value and the actual value. So basically the intention is find the value of a and b so that this particular difference, right, this particular difference which is the actual value minus the expected value or predicted value that is coming through this mechanism, the difference between the two, which is nothing but this error, when I am taking the square of it. Why I take the square? Because error could be positive as well as negative. I don't want the error to be neutralized off, so that's where I am taking the square of the error. When I take the square of the error, that particular square of the error should be minimum most possible. So I want to minimize the summation of all these things. So this particular method where I am minimizing the error between the expected and the actual values is what is called as the least squares, ordinary least squares method of finding out the value of a and b, which minimize the error between the actual value and the expected value. That is what is getting into this regression model. And just to give you a quicker understanding of this, the way we compute the values of b and a from this, the value of b comes out directly as the slope of that particular line. This is b is nothing but the slope of the line of regression of y on x. So the way we compute the value of b in this process is we take the covariance between x and y divided by the variance of x. That is how we compute the value of b in this particular equation. So let me try it on the data. On this data, when I am trying it out, if at all I want to go with the b, the equation for the regression equation between the two, which is nothing but, to understand it much better, whatever is this trend line that has been drawn, that particular trend line, the equation associated with this particular trend line is what we call as the regression equation. And in this case, these are the errors, right? These are the errors, whatever this particular point is from this particular line. These are the errors that are coming up. So what we are saying here, that particular error, depending on the choice of b and a, I take all combinations of a and b. There I am trying to find out what particular combination of a and b will minimize the error between the actual value and the expected or predicted kind of a value. And what we are saying is that comes out always through this formula of covariance between x and y divided by the variance of x. We have already taken the covariance between x and y divided by the variance of x. We have the standard deviation of x here. So I take the square of that, which will give me the variance of x. So it says the b value is 0.139. Okay, from this equation, I got b is 0.139. That is the equation. So basically my equation is y equal to a plus bx. That is the regression equation. And the way I am computing that a and b is computed directly as the covariance between x and y divided by the variance of x, which has come out to this much. And the way I take a is I take the mean of y minus the b times the mean of x. It is nothing but a equal to y minus bx, and one such instance is a equal to y bar minus b times x bar. So here I will take a, which is y bar, which is the mean of the profits minus b times the mean of the sales. That is what is the value of a, and a is, let's say, minus 43.1. So in this case my regression equation will be y equal to minus 43.104 plus 0.13902 times x. This is the regression equation between x and y, profits and sales. This is the regression equation between x and y. So this is called as the slope of the regression equation, or probably in our in some cases we even use a word called beta to denote this. So these are the various names that are associated with this particular regression equation, right? Now once I have this regression equation in place, I can even look out for reworking on the data using this regression equation. Means predicting, if I had applied this particular equation to my historical data, what could have happened? If I had applied this historical data, what could have happened? So I will insert a few more columns here. right? I'll insert columns by shifting the cells to the right. Okay, few more columns I am inserting on this data. Okay, now what I am trying out is, in case I had predicted using this particular equation, it's like backtesting. I am predicting the value of y using this equation, a plus b times x. What is x here? A plus b times x. That is what is the value of y here. Fair enough. So this should be the profit going with that particular equation. So these are the various profits if I am assuming that these are my sales. Now the difference between the actual and the predicted is what is the error, and I always take the square of the error. The actual profit is this one minus the predicted profit is this one. Actual profit minus predicted profit, I am taking the square of it. This is what is the error. And what I am trying to find out is the sum of squares of error. Sum of squares of error, which is nothing but the summation of all these numbers, is what is the sum of squares of error. My intention is, if I use any other combination of A and B, I will get this error, sum of squares of error, much heavier than this number of 2.77 million. This is what is the sum of squares of the error, which is nothing but, from an interpretation standpoint, on this graph, this line, the distance between this line and this point vertically, that is the error. You square up that error and you add up for all these points. That is what is the sum of squares of the error. And when we are talking about a regression equation, which is found by using the b value as the covariance between x and y divided by variance of x, and where you have found out the value of a, which is otherwise the terms wise, b is called as the slope and a is called as the intercept, which is a is found out by subtracting x bar times b minus the y bar. So we are getting the regression equation, and no other error can be smaller than this particular value. So this is what we call as the regression coefficient. So as a regression coefficient, my b is 0.139 and a is minus 43. So as an interpretation, if I am looking at the slope, it's simply telling me that if the sales increase by $1, the profit can increase by $0.13. That is what we interpret the slope. If the sales increase by $1, the profit will increase by $0.13. So sales up by $1, profit up by $0.13. That is what is the interpretation of the slope. When it comes to y-intercept, when the dependent variable is 0, when the independent variable is 0, the dependent variable is minus 43. Means when the sales are 0, there is a possibility that the profit is negative, taking it to minus $43. That is what is the interpretation of the interceptor. So these are the two things that we have to keep in mind. Now, as I said, every calculation which we are doing, we have to look out for the significance of that calculation from a statistical dimension. So, now a bit of more extension to this. Apart from computing the regression equation, we also have to get into the concept of how we will use a term called coefficient of determination, which is nothing but, see, the dependent variable in actual is varying to this extent. The independent variable is also varying to some extent. Right? When I am saying varying, the variance part of it. Now, what extent of this dependent variable, variance or fluctuation, is taken care of by the independent variable? Not just the average. What I am looking at is what extent of the variance of the dependent variable taken care of by the independent variable. The other way I have to put it is, when I have looked at the dependent variable in isolation, the standard deviation came out to this much. When I have looked at the dependent variable in isolation, the standard deviation was this much, or the variance was the square of this much. So this is the variance of the dependent variable without taking the help of the independent variable. But when I am using my regression model, this is what are the values of the dependent variable. These are what are the values of my dependent variable. Now all I want to check is what is the variance in case of the predicted variable. In case of the predicted, what is the kind of standard deviation that is present? The same logic I can use. I can find x minus x bar squared, divide by n minus 1 for this. Rather than that, I can even use the formula of standard deviation. So, taking the original values variance versus taking the variance of this particular predicted values. So if this is the standard deviation, probably the square of this is the variance. So what we are saying is, when the original data had a variance of almost 77,000, when I am doing the predicted data, when I am using the formula, regression formula to predict the data, the variance of that is only this much. So the unexplained variance, this is what we call as explained variance. The variance of the predicted terms is what we call as explained variance. So based on this, I say unexplained variance. Unexplained variance is the difference between these two variances, 77,000 minus this. So unexplained variance will come out as 28,076. That is what will come out as unexplained variance, and the 49,000 is the explained variance. So what we are simply talking of is the coefficient of determination, otherwise called as R squared. Coefficient, so if the original was, if the dependent variable was having this much of variance, how much of it is taken care by your independent variables? So that is what is the determinant of coefficient of determination, otherwise called as R squared, and it is simply calculated as whatever is the variance of the predicted variable, which is explained variance, divided by the total variance in the original data, which is coming out to almost 63.72%. That is the coefficient of determination. So simple way of putting it is, what proportion of the variation in the dependent variable is taken care by the independent variable. So this is working out to almost 0.63, which means 63% of the variation in the dependent variable is taken care of by the independent variable. Then we have one more thing to talk of in this context, and the other way you should look out, at least in case of single independent variable, is you try finding out correlation squared, you should get the same number. You try out the correlation squared, which is nothing but r squared, at least in case of single variable kind of scenario. This coefficient of determination, which is found out by looking at the total variation and explained variation, dividing the explained variation by the total variation. In this case, at least for one variable, you see that kind of matching occurring quite comfortably. Then one more thing that is worth understanding in this context is the standard error of the estimate. When I am taking the standard error of the estimate, the simple way I can look at it is, we got the error term here, we got the error terms here, these are the error terms. I divide these the sum of these error terms. I divide the sum of these error terms. We got already the sum of squares of the error, right? So that sum of squares of the error, I divide it. So I take the error term. It's as good as saying I take the error term. So if I don't take the square here, probably only the error term if I take. What is the error term here? The actual minus the predicted. I don't want to take the square root of it directly because we have a positive as well as the negative values. So if I take the error terms directly, right, I take the error term directly and I take the standard deviation of the error terms. Simple way of understanding the standard error of the estimate is nothing but the standard deviation of the error term. When I am taking the standard deviation of the error term, right, this is the standard deviation of the error term. So this is what is called as the standard error of the estimate. We'll see where we will use it again. The standard error of the estimate here is nothing but the standard deviation of the error term, which is somewhere around 167. We'll use this standard error of the estimate while doing our prediction values, the interval for our predicted values. But for the time being, one more important calculation that is necessary in this context is the calculation of the standard error of the estimate. So if the value of this error is very, very small, the estimate is more and more an appropriate estimate, but as this error increases, the value of the estimate becomes more and more poorer. Now, the next important thing is, yes, we have got our regression equation, minus 43 plus 0.139 times x. Now, the next thing is we have to test for whether the regression coefficient is statistically significant. Because just like the way we have done it in case of correlation, here also I have to test whether the regression coefficient is statistically significant. So again, from that dimension also, I'll say the null hypothesis for me will be b equal to 0, which means the regression coefficient value is as good as 0, whereas the alternate hypothesis will say the regression coefficient is not equal to 0, which means it is statistically significant. So what we'll do is, for each of the regression coefficients, there is a standard error that is computed. Generally, when I use any kind of statistical tools, they compute the standard error for us. So what I can do is, I can look out, probably I'll use a direct regression generating procedure. From there we can try doing some interpretation. So I'll go here, I'll use a regression mechanism. Okay, I'll use a regression mechanism, what kind of output it generally generates. So based on that, we'll see how do we interpret the things. So my y values are probably the profits, which are from here to here. My x values, which are the sales, which are from here to here. And based on this, let's say if I am generating something, okay, this particular output that gets generated, generally this is generated by most of the statistical packages. So here what we are looking at is some of the things which we have already calculated, the correlation. So this is nothing but the correlation, which we have calculated it as 0.79, right? The correlation of our data got calculated as 0.79. Similarly, we have few more elements there. We have computed the R squared through a different mechanism. So even this is matching. Now, the standard error 168, actually whatever we got as standard error 167, okay, I have to take the standard, okay, some small calculation issue. So the standard error of the estimate is coming out to somewhere around 168. The other way I can look out for the standard error, right? The other way I can look out for the standard error is to do a better thing. I can take, I have got this unexplained variance. This is my unexplained variance part. Here also, so the variance in the estimate, this is the standard deviation in the y values. Okay, let me not take the standard deviation directly, right? Even if I take it, not an issue. See, rather than taking the standard deviation directly, probably I'll take it at a slightly higher level. I multiply this by n minus 1. I multiply whatever the variance that I have got by 99, which is nothing but I am taking only the sum of squares. Only the sum of squares rather than looking at the standard deviation per se. So the sum of squares, here it is probably 7.6 million. This is what 7.66 million is the total sum of squares which I am getting through this particular process. Similarly, this also I will take n minus 1 only into multiply it by 99 instead of, so the explained sum of squares is this much, unexplained, the total sum of squares is this much. So from here I can very well get the unexplained sum of squares. Instead of using the word the variance, I will talk about unexplained sum of squares, which is coming out to 2.77 million, which is what is being shown here, right? Now from here what we are trying out is, okay, this table, when I am talking about the same standard deviation and variance of the original variable and variance multiplied by n minus 1, because when I am dividing, when I am arriving at the variance, the sum of squares of deviation from the mean divided by n minus 1. So if I don't divide by n minus 1, I will get the sum of squares of deviations from the mean. So I am taking it for the original variable, I am taking it for the predicted variable. So the predicted values, I am getting this much as sum of the squares. So the difference between the two is the unpredicted value of sum of the squares. Now what we are saying is, okay, this is the unpredicted value, and because we are talking about two variables, we are talking about two variables x and y. Here I will introduce you to the concept of degrees of freedom. The degrees of freedom, in a simple way to understand, depending on the number of records, the number of observation, the sample size. So the degrees of freedom for the total data is n minus 1. So if I have 100 records, the degrees of freedom is 99. Out of that, I split this degrees of freedom between the independent variable, between the regression variables and the residual part. And always remember, the degrees of freedom for the regression variable is always the number of independent variables. So in this case we have only one independent variable, but when we look at multiple regression we may have more than one independent variable. So the degrees of freedom is 1 for the regression variable, and the remaining degrees of freedom will go to the residual. So overall degrees of freedom is 99. So if it is one independent variable, 1 degrees of freedom goes to the regression part, 98 degrees of freedom will go to the residual part. In a way, if there are k independent variables, so the degrees of freedom for the regression is k, degrees of freedom for the residual is n minus k minus 1, because overall degrees of freedom is n minus 1. Now what we do is, here out of this degrees of freedom whatever we have got, here also you see 1 is coming for the regression, 98 is coming for the residual, and total is 99. So these are the sum of squares from the sum of deviations, sum of squares of deviations from the mean. These are called as sum of squares of deviations from mean. Regression means the predicted, take the predicted values. This is take the error values, the same work, and this you take it as the original values. So those are these three elements, right? And when I am doing the sum of squares of the predicted divided by the total, that is what is coming out to r squared. If we see here, sum of squares of the regression divided by the total is what is coming out to r squared. For time being we can ignore this, because this will be applicable only in case we have a multiple regression where we have multiple independent variables. In this example I am discussing only about single independent variable, but slowly later I would even cover the multiple independent variables kind of a concept. So there I will discuss about this adjusted r squared mechanism. Now, so we have looked at this aspect also, we'll come to these things, but before this look at some more things which we already know. The intercept is minus 43.1, which we are able to calculate. The slope which is covariance between the x and y divided by the variance of x, which has come out to this. Now these are the standard errors which are typically given by any kind of statistical package. Now from here, for testing the significance, what we do is we compute the t values. For testing the significance, we compute the t values of the estimate. The way we compute the t values, is for every coefficient, you take the coefficient divided by the standard error of that coefficient, right? That is what is the calculated t value. Otherwise we call it as t statistic for each observation. So this is what the system has already computed, but even if I have to know how it is done, the coefficient divided by its corresponding standard error. So this is how the t values are computed for both. These are my computed t values for each of the coefficients. So for both A as well as B. And even in the real terms, the hypothesis testing, whatever we are doing, we are saying, okay, A equal to 0, B equal to 0. Whereas null hypothesis says any of them, at least one of them, A is not equal to 0, B is not equal to 0. I am doing the test in one single shot. So the t statistics for each of them are computed. Now every computed t statistic need to be compared with a critical value. So if I am going with a 95% kind of a confidence interval, what is the critical value? If I am taking the 5% level of significance and 99 degrees of freedom, my calculated value is 1.98. Right, 1.98 minus 1.98 to plus 1.98 is the typical interval for saying that you cannot reject the null hypothesis. Any calculated value outside this interval, you can very well reject the null hypothesis. And in your case, both of them, so the first one is below minus 1.98, the second one is above 1.98. So both of them are outside this particular limits. So you are rejecting the null hypothesis in this example, and you are going with the alternate hypothesis, saying the coefficients whatever are there, A and B, they are significantly different from 0, because if we look at the number per se, we had the slope as 0.13. If it is 0.13, I may always have a doubt whether it is significantly different from 0 or is it not different from 0. So to address that part, we are looking at the hypothesis test, finding out the t value and seeing whether the t value is outside the confidence interval limits or is it within it. If the computed t value is within the interval, I cannot reject the null hypothesis. Otherwise, I am going straight forward to reject the null hypothesis and going forward for the alternate. So even if someone is asking what is the possible interval for this coefficient, the next part is what is the possible interval, confidence interval for the coefficient. Confidence interval for coefficient, all I am looking at is take the coefficient value plus or minus the whatever is the t value or whatever is the interval value, critical value, times the standard error. critical value times the standard error comes out as your confidence interval. Here also, if I am seeing, the system has already computed the confidence interval for us, but if I want to manually compute it for this, okay, the p value plus whatever is the t value, let's say this is the required t value as per 5% level of significance times the standard error. So we are seeing that we are getting this 0.118 which has been given by the system also. Even on the higher side, if I have to see, take the coefficient plus whatever is this border limit 1.98 times the standard error. So it is coming out as 0.16005. So this is the 95% confidence interval, means I can say with 95% kind of a confidence that the sales, the coefficient for sales lies between 0.118 to 0.16, means there is a 95% chance that 0 does not come into the interval. So because 0 does not come into the interval, I can very well say that the value is significant, that the coefficient is significant, because the 95% interval does not contain a 0. If the 95% interval contains a 0, then I don't have much of an evidence to typically reject the null hypothesis, and probably I may be forced to go forward with the null hypothesis itself. So that is one more way. So all of them will give me the same. Either I take the t value and based on the t value compare it with 1.98 and see whether it is outside the limit or within the limit, and if at all it is outside the limit, reject the null hypothesis and go with the alternate. Otherwise, don't reject the null and you go forward with the null hypothesis itself. So now that we have this particular equation, so if someone says, yeah, I'm planning a sales of $1,000, I'm looking at a sales of $1,000, then what should be the profit I should expect in this particular business? Then I can very well say, yeah, you should then look out for A plus BX, this times 1000. So going by the industry trend, if at all you are expecting $1,000 as your sales for the current period, then probably you should expect around 95 for every $1,000 of sale, then probably you should look out for $95 as a part of your profit projection. That is what is being is the major help that comes out with the regression equation. And even this predicted values, they go with a confidence interval. Now that I am able to predict this as the scenario, if at all I have to build an interval around this, so for this confidence interval, so if I want for a predicted value, I am taking the confidence interval, that is where the standard error comes into picture. So how is the standard error coming up? Before I go slightly more into it, yeah, we know how do we get this. So the other thing is, we call it as mean sum of squares, which is nothing but the total sum of squares divided by their degrees of freedom. So this is nothing but the 2.7 million divided by 98. This is what is the mean sum of squares that I get with respect to the error. I take the square root of that mean sum of squares. I take the square root of the mean sum of squares. That is what will come out as the standard error in my case. So using that standard error, if I want to go with the confidence interval for predicted values, my predicted value in this case is already coming out to the 95 in this case. Now using this, I may want to go for a confidence interval for the predicted values, we already have the forecast, whatever is the error that is existing, standard error that is existing. So what you typically do is, so if I have to go forward and compute the confidence interval for the predicted, right now we are having a predicted value of 95. But even for the predicted value, if I want to compute the confidence interval, first we have to compute what is called as the standard error of the forecast. The standard error of the forecast, which is a variance part which I get, you take the mean sum of squares of the error, or probably the standard error of the estimate squared, into 1 plus 1 by n, the number of records that are there, and into x minus x bar for whatever the x you want to predict. In our case, for 1000 I wanted to predict. So take x minus x bar squared divided by n minus 1 into the variance of x. So this will give me the standard error of the forecasting error. So based on this particular forecasting error, I will form the confidence interval. So what you do is, now that I have this value, I'll say the standard error of the forecast is nothing but the standard error of the estimate squared, multiply it with 1 plus 1 by the total number of observations, which is 1 by 100, plus x minus x, I am taking it as 1000. For that I want to do the prediction, minus, you look out for whatever is the mean of x, this is x bar, x minus x bar squared divided by, again, n minus 1, which is 99, n minus 1 times the variance of x. The variance of x is coming out to, probably I'll take the square of this directly. So this is what is coming out, right? And I'll close the bracket out here, which is coming out as, this is what is an adjustment, small adjustment to the forecast. So based on that, I take the standard, the square root of this, a small adjustment will come. So I take the square root of this and use this as an input. 169.25 will typically go as input to my prediction part. So whatever I got, 95 minus the t times 1.98 is the t times the standard error of the forecast, to profit plus t times the standard error of the forecast. So I can say my 95% confidence interval for the profit is minus 239 to 431, which means if the standard error is very, very high, there is a good chance that our predicted values are more and more widely going off. That is one more thing we have to be understanding. The more and more is our standard error, the more wider and weird will be our predicted value. So though we have got the predicted value as 95, if I am trying to build a 95% confidence interval over that predicted value, it is coming out that it will lie between minus 239.91 to 431.75. So there is a huge gap that is getting created. So we have to see that the standard error is going much and much lower. The accuracy of our predictions go more and more better off. So basically when I am using any other improvised model, probably a multiple regression model or something else, my intention should always be to make sure that the standard error of the estimate comes down so that a better interval can be built around that particular scenario. That is what is one main thing that we are looking at. Now, the other important aspect that surrounds in this, which we call as analysis of variance, to a large extent we have understood the various aspects of this. So for the predicted variable, I take the sum of squares from the mean that I am computing here. For the error between the predicted and the actuals, I take the sum of squares from the mean. That is what I get as a residual here. And the original values, I take the sum of squares from the mean, I get this. So basically we call them as, this is the regression sum of squares, this is the sum of squares of the errors, or sometimes people call it as residual sum of squares, and this is called as the total sum of squares. And as I said, when I want the r squared, it is nothing but regression sum of squares by total sum of squares. That is what is my r squared. Standard error is nothing but the square root of mean sum of squares. Mean sum of squares of the residual. Mean sum of squares of the residual is what is equal to the standard error of the estimate. Based on the standard error of the estimate, we even compute the standard error of the forecast using the formula which I have talked of. Now, the other important thing is testing the goodness of fit of the model. Testing goodness of fit of the model. So here we are going ahead with a comparison between the regression and the residual. The variance that is getting generated between the regression as well as the residual part. And for that I look at the mean sum of squares part. So basically here the test that is typically going forward is I make a hypothesis saying there is no difference. Null hypothesis is there is no difference between the regression and the residual variances. So variance of regression is same as variance of residual, whereas the alternate hypothesis says no, this is not the same. Variance of regression is much better than the variance of residual, or vice versa. So from that dimension I take what is called as an F test, which is the variance of the regression divided by the variance of the residual. That is what is the F test I am performing. So in this case the F test comes out as the variance, which is the mean sum of squares of the regression divided by the mean sum of squares of the residual. What is comes out as the F value. And based on this F value, I will look out for the table value, which is the critical value compared to F. If I am looking at a 5% level of significance, then probably I am looking at the degrees of freedom for both of them. Let's say the first regression is having a degrees of freedom of 1, residual is having a degrees of freedom of 98. So the table value is only 3.93. So the critical F value is 3.938. So what we are looking at is because f cannot have negative value. We are looking at as long as our calculated f lies between 0 to 3.938, I cannot reject the null hypothesis. I have to go with the null only. But if my calculated value lies outside this range, I can reject the null hypothesis and go with the alternate. Here we got 172, so I am rejecting the null hypothesis and going with the alternate hypothesis itself. So here I am saying there is a huge difference in the variances between the regression and the residual. Means regression is able to explain a significant portion of the variance of the dependent variables. The regression model is able to explain a significant portion of the variance of the dependent variable. The regression model is a better fitment kind of a model. So when I am computing the f value, if I am able to see that my calculated f is greater than whatever is the critical value that is associated with the f, I can directly go ahead with saying the model is a goodness of fit kind of a model itself. Now the standard error, when I have taken earlier, I got it like this, right? I should not take the standard deviation directly. I should take the sum of squares of the error, whatever is the error term, right? This is the sum of the squares of the error term. So if I had done it as the sum of squares, instead of directly using the standard deviation, if I had done the sum of squares of the error term, don't divide it by n minus 1 here, divide it by n minus 2. I divided by 98 instead of 99. Earlier, because I have divided it by 99, I got a slightly different value, but I divided by 98. So which means the sum of squares of the errors divided by n minus 2 is the standard error of the estimate. So dividing it by 98, so I should write the standard error of the estimate is sum of squares of the error divided by n minus 2. This will give me the variance. So I take the square root of it, I get the standard deviation, which is the standard error of the estimate. And as I said, even you could have done the mean sum of squares of the residuals, the square root of that, even that should give you the standard error of the estimate itself. So I take the square root on the top of this, I should get the same number matching with this. So 168.41, that has matched even with this kind of a scenario. So I am computing all these. So I should be comfortable in terms of filling up this entire table, right? The F statistic, and how do I use the F statistic in terms of comparison. So all these things have to go as a part of our typical analysis. So whenever I am getting an F statistic, I will compare it with the critical values using the degrees of freedom, and if my F value is greater than the critical value, then I can very well reject the null hypothesis and I can very well go with the alternate hypothesis itself. So at least for this example, I can very well go ahead saying the regression equation is something like this, which is what is the linear relationship between the profits and the sales. Now, if I have to look at some important limitations kind of aspect in this scenario, whatever is the relation, this is based on the data that I have got at a particular point. Right now, let's say I have downloaded what are the sales of various companies and what are the net profits of various companies. So at this point, this is the relation. But it may so happen that across time, if I take it after 6 months, probably this relation may be existing or may not be existing. So that is one more thing. From each of the periods, whatever the estimate that I am doing may not be applicable to the next period. So means the A and B could vary with respect to time. That is what we typically call as the parameter instability kind of a scenario. The parameters A and B may not be constant across time. And see, in some cases there may be many other factors that may be impacting, not just one single factor. It may be many other factors also coming into picture. Why only sales? Probably I should look out even for the costs. I should look out for something else also. So I should look out for the capital or debt versus equity capital. Some such kind of things also I would like to look out, or put together they are going to explain my profits much more better compared to taking only the sales. And it may so happen that there could be some problems associated with heteroscedastic kind of a data. See, what does that mean is, probably the relationship is holding true, let's say until the sales of 0 to 1000 or 0 to 2000. But for sales which is above 2000, the relationship is not holding true much better. So what could very well happen is we have to test it. That is what is called as heteroscedasticity. Scedastic nature is nothing but variance. Scedasticity is a term which is used for variance. So the homogeneous variance does not exist. Heterogeneous variance is coming up. If I want to talk slightly better about it, if we see here at the lower end, I see most of the points, let's say if they are very close to the line, almost some of them are on the line and some of them are very close to the line. Whereas as the values of the sales are increasing, I am seeing that the points, let's assume they are deviating very heavily from the line. That is what is an explanation of heteroscedasticity. So even that has to be taken into consideration before using our model quite effectively or quite extraordinarily. Right? If at all I have to use this model for prediction purpose, it has to come out from this particular dimension also. So that's all I would like to look at in this session. Of course, I did not cover one aspect in this, the p-values, which I'll take up when I deal with the multiple regression. The same way I did not take up the adjusted R squared, which also I would take up as a part of the multiple regression scenario. But otherwise, I hope everything else is comfortable to you in terms of understanding the concepts of correlation and regression. In case you have any further queries regarding the same, you can get back to me by giving me a call on the number that I have provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.